Hi there, folks. If you're watching this video, first of all, you are awesome. Thank you. You are here because you are interested in learning or knowing or acquiring tastes of whatever stuff. Now, the first portion of this video, though, is going to be stuff that you might have already seen if you were in class and whatever else, and you looked at the front page and you reviewed all that. So that's just one thing there. So you can fast forward to whatever you need to. So I'm going to go over this front stuff again. It's going to take a while. And then I'm going to go over these actual problems here and here and here and all that stuff. Some, they don't fully fulfill what you might want to write down, but I can't help but think that you will not completely understand these problems once you get out of it at the end of the day. Okay, so I'm just going to jump right into it, and I will try and go as quickly as possible. And I'm actually going to admit something right now. I already recorded this video once. Now, you might not end up knowing it because I don't know if I'm going to upload it or not, but I actually uploaded a version, or I created a version of this video, and go figure, I have done this before. I did not enable my microphone. And trust me, right now, I am not a happy person from that. But that's a me problem, and that's something that I'm working on for the fact that I can't remember to enable something. But that being said, as I'm drawing this, hopefully you're drawing it on your paper if you don't already have it drawn. And we'll get right into work. Last time it took me an hour. I'm going to break an hour's time easily. Or, well, not easily, but it's going to take me some time. Okay, I'm going to start. So I drew these unique different quadrilaterals here. They're unique by their properties alone. They don't all have the same kinds of things. So let's start talking about each of them by properties, and I'll start labeling what all of them mean there. Starting with the parallelogram here. Parallelogram has opposite sides that are parallel and congruent. Both parallel and congruent. So, by the way, if you are writing this down, you're going to have to pause because I'm stream flowing through this for you to help you out. Opposite angles are congruent. Consecutive angles are supplementary. And finally, diagonals bisect each other. Okay, so what that all means there, and I'm going to color code all of these here. Let me start with opposite sides are parallel and congruent. Opposite sides are parallel and congruent. Well, this is what they mean. I'm going to draw where they're represented, really, is what I meant. Opposite sides parallel and opposite sides congruent. The tick marks would represent that or whatever else. So there you have that in a parallelogram. Once you have that, you know you have a parallelogram. Trapezoid and kite don't have that stuff already right there. Opposite angles are congruent. Opposite angles meaning if I'm looking across the way, like, hey there you are. Right? Opposite angles are congruent, so this guy is congruent to that guy, and this guy is congruent to that guy. Check, check. Consecutive angles are supplementary. Now, consecutive means like right next to. So there's an angle right here. This guy is consecutive in sequence with it. These are supplementary to each other, so these always add up to 180 degrees in a parallelogram. And really the reason is, if you think about it, here's a parallel line, here are two parallel lines, and here's a line transversal going through those two parallel lines. Right here, you're looking at same side interior angles, and that relationship right there, these are same side, not really drawn very well, these are same side interior angles, and those are always supplementary. Not just these two, but these two as well, because these two are parallel, and these two are parallel with this transversal, so these are supplementary, and same with these two right here. So consecutive angles are supplementary. Another way to look at it really is this angle is also right here, right? Corresponding angles. So these are supplementary, you know that. And the last one, diagonals bisect each other. And what I'm going to do here is draw you the two diagonals. I just want to make sure you know and remember what bisect means here. Here's a diagonal in this section. Here's a diagonal in this section. The diagonals are the segments drawn from vertex to vertex on opposite sides of each other. So while the opposite angles are congruent, you can draw the diagonal through there as well. The diagonals bisect each other means that this diagonal creates two congruent segments here and here in that diagonal. And this diagonal creates two congruent segments here and here in this diagonal. So it's kind of cool. You get that. And the place where they intersect is that very midpoint. This is the midpoint of this diagonal. This is the midpoint of that diagonal. Okay, the area formula, I'm just going to give it to you here. Area is base times height. The only thing that, and trust me, I wrote and said a lot more in my other thing. You can even, I'll upload the video and you can just watch it and see I'm on pause for a little while. No, I'm talking during it. But what it really is you have a base. You select your base, maybe a length that you have. The height will be that length of that thing between your two bases. It's perpendicular to your bases. Remember, your height is not the slanted one right here. Your height is the one perpendicular to it. So you have that base, you find that height, or the other way around, you will get the area of your parallelogram. Okay, the kite has some certain properties here, such as, and I don't know if this is the best word to use, but I say neighboring. I said in the last video too. Neighboring sides are congruent. The other thing is that one diagonal is a perpendicular bisector of the other diagonal. So neighboring sides are congruent. I mean, you can see which ones are congruent. And normally, though, we draw the kite facing the other way. You know what I mean? So normally, you'll see it like that way, and these will be congruent. I'm doing it sideways to maximize my space I have. Those sides are congruent. Those sides are congruent right there. They're like, hello, neighbor. I can see you. And hello, neighbor. These guys, for some reason, aren't neighbors. They're frenemies. So neighboring sides are congruent. And then one diagonal is a perpendicular bisector of the other diagonal. So what that means here, and this is important to make sure that you know what a diagonal is. A diagonal is not always diagonally faced. You think of diagonal like this, like kind of up, kind of right, whatever else. Well, these ones are going to be straight up horizontal, here and here. All a diagonal needs to be is a segment going from one vertex to the other that are facing each other oppositely. They're opposite angles. And so, in this case, that's what you have. You have two diagonals there. This longer diagonal, and it's not always longer, but the one that's uneven, this diagonal will be a perpendicular bisector of this diagonal. So what's going to happen is it'll create this perpendicular segment here. And it's really perpendicular everywhere, all the way around, but ignore that. I just need one. And if it bisects it, it creates congruent segments here and here. So there's your kite. And I'm going to do a little bit more because I need to talk about how the area is derived here. The area itself, it's not D, the area is half the measure of the product of your diagonals, D1 times D2. And you might ask where those are. Let's go ahead and label them. If I call D1 this purple diagonal right here, that is D1. If I call D2 the red one, I'm just going to keep it red. D2 is, by the way, it's the entire length. It's not just one part of it. There's all of D2, there's all of D1. Area's 1/2 of it. And really, I mean, I'm not going to restructure it and everything else. I did in the other video, like I said. But really, D1 is like the base of a rectangle over here, and D2 is like the height of a rectangle. Take the area of that rectangle, you get it right here. Well, the kite is half the area of that rectangle. Okay, that's all it is. Okay, trapezoid is unique in its own way here. It only has one set of parallel sides. Only one set of parallel sides. I'm going to call those ones my bases. Okay. The only other thing I'm going to put is the leftmost angles are supplementary and rightmost angles are supplementary. I'll explain both. Okay, only one set of parallel sides, the bases. So my bases I want to put right here and here. And in fact, we label them as such where you can tell these aren't equal. These are not the same base lengths. This is B1, B2. or whatever. Name them whatever you need to, but they cannot be the same variable because they're not the same length. I'm using these specific ones for the area formula, though. Leftmost angles are supplementary. So if it's drawn like this, where your bases are on top and bottom, I'm talking about these two guys over here. So there's the base one. Leftmost angles are supplementary to each other. I should have put. So this plus this equals 180 degrees. If you think about it, it's the same kind of thing as I did with the parallelogram up top. Parallel sides cut by a line transversal. These are same side interior angles. They are supplementary. And same with these guys right here. This plus this also equals 180. Now, these aren't necessarily the same. In fact, they can have zero relationship whatsoever. Same with these guys right here. So I'm dividing this in half and looking at, excuse me. Sorry, I just sneezed. And I'm looking at these two guys are supplementary. These two guys are supplementary. Now let's go to the formula. The area is half base 1 plus base 2 times, let me do that again. Get some more room. 1/2 B1 plus B2 times height. Breaking it down. Thinking about it here, your height has to be the altitude, that perpendicular segment there drawn between your bases. There's H. So you can get that. Again, if you make a right triangle out of this thing, you can use Pythagorean theorem, trigonometry. You can do whatever you need to find that height. Or you're given the height and you define base length here. But really, I want you to think of this here, 1/2 B1 plus B2. I want you to think of this as like, I'm trying to take the average of my base values. Taking the average of them will grow this base length just a little bit. And it'll shrink this base length just a little bit. And you'll see here, I've kind of made a rectangle. Well, I did. I made a rectangle with a new base length. That's the average of my two. And what was lost here was gained here. What was lost here was gained here, if it was really drawn to scale. So it's really just the area of a rectangle, but different base lengths there. Okay. I'm just kind of going to, well, I'm not going to move on yet. I wanted to say two more things, and they're going to be underneath parallelogram. If you want to write them as footnotes, that would be great. I'm going to talk about really what specifically a parallelogram has versus these other two shapes here, a rectangle and a rhombus. A rectangle is a parallelogram. Yes, it is. Don't say no, it's not. Yes, it is. A rectangle is a parallelogram with, oh, by the way, in addition to, it has 90-degree angles. Okay, and I'll explain that in a second. And a rhombus is a parallelogram. I think most of you guys knew that. With all sides congruent. Okay. Now, here's really what that means. Let me first break it down simply like this. All men are human, I think, but not all human are men, right? All men have the same properties as a human does, but not all human have the same properties as men, because women don't all have the same properties or characteristics or features or hobbies or whatever as men do. I shouldn't say hobbies. Rectangles have everything that parallelograms do. In a rectangle, opposite sides are parallel and congruent. In a rectangle, opposite angles are congruent, 90 degrees, by the way. Consecutive angles are supplementary, because 90 plus 90 is 180. And the diagonals do bisect each other. A rectangle is a parallelogram, but in addition to not just being a parallelogram, all the angles are also 90 degrees. A rhombus is the same way. It has all these things just like a parallelogram does, but all sides happen to be congruent. In this case, in a parallelogram, only opposite sides have to be congruent, here and here, not necessarily all of them. And here's another shape, the only other quadrilateral I really want to talk about, which is a square. A square is a rectangle with all sides congruent. And a square is also a rhombus. We don't really see it as that as much. We normally associate rectangle with square and rhombus with parallelogram. It's not necessarily that different. It's a rhombus with 90-degree angles. So you'll see the only difference between a rectangle and a rhombus is that a rectangle has all sides, or it has 90-degree angles, and a rhombus has all sides congruent. Otherwise, they're just like parallelograms. Actually, I take that back. A square and rhombus also have perpendicular the diagonals not only bisect each other, but they're perpendicular bisectors, and all segments of the diagonal are congruent. So there you go. Okay, I'm going to move on down here. We're talking about coordinate geometry now. Slope-intercept form. That's that y equals mx plus b, where m is your slope and b is your y-intercept. And again, I get to make that joke because y-intercept starts with b, right? Haha. The only thing I want to mention about parallel and perpendicular lines here is that parallel lines, if you're trying to find like the equation of a line that's parallel to the other one, you need to make sure you have the same slope. So if this is like y equals 6x minus 9, the other one needs to be y equals 6x something as well. It needs to have the same slope. That's what will make them not intersect. This goes up 6 over 1, up 6 over 1, like that. The other one needs to have that same slope and never intersect. Perpendicular lines need to have the exact opposite effect. If you have a slope like this, the other one needs to go so oppositely that it creates a perpendicular segment. And it's not just opposite, but it needs to have a slope that's an opposite reciprocal. And what that means, opposite means negative. Reciprocal means inverse. I don't like to put negative reciprocal, though, because I want you to think that even if you have a negative slope, you need to get the opposite of it, which is positive. So if like I had a slope, for instance, of like p over q, where p and q are just random integers, my opposite reciprocal slope, that's the perpendicular symbol, by the way, is negative q over p. So I get the opposite of, if this was positive, it's negative now. If it was negative, it's positive. And I flip these guys. So now what was p is now q, and what was q is now p. So if my slope was like 4, then my opposite reciprocal is negative 1 over 4. 4 over 1 and negative 1 over 4. You can see how those are opposite reciprocals. Okay, midpoint formula. I'm going to spare you some time here before I was getting a little too fancy with it in my other video. Like I said, I want to save time. If I have but I need the 2 points, x1, y1, and if I have the point x2, y2. I want to find the point that's right in between. That point is the average distance away from 0. So if this is some distance away, x1, this is x2 away, this is right in the middle of that. I got to take the average of it. So my x values will be x1 plus x2 over 2. Remember, just like trapezoid, taking the average of the lengths to get that one that's right in between. And same with the y's, I need to do y1 plus y2 over 2. Okay, so that's the midpoint formula. I'm going to, like I said, I want to save you time there and just get you that. Distance formula. Assume we had x1, y1, x2, y2 again, and I want to find the distance between these guys in purple. Let's call it d. That distance, I'll give you the formula first and just explain it, is the square root. It's a bad square root. Square root of x2 minus x1 squared plus y2 minus y1 squared. Really, all it is Pythagorean theorem. I want to see the distance between x1 and x2. That is x2 minus x1, right? The distance between 7 and 2 is 5, 7 minus 2. So the distance between x2 and x1 in the horizontal direction is x2 minus x1. The distance between y2 and y1 is just y2 minus y1 for the same reason. If this is like 5 and this is 1, the distance between it is 4, 5 minus 1. So now you're looking at, really, you're just looking at a right triangle. Here's a right triangle. Here's a leg. Here's a leg. Here's the hypotenuse. Hypotenuse can be found using Pythagorean theorem. A squared plus b squared equals c squared. In this case, d squared. Take the square root of that, and d is the square root of that plus that. I know I'm making it messy now. But d equals the square root of that and that. So if this doesn't make much sense to you, just really think Pythagorean theorem here. You don't need to get too fancy with it. Whatever you write in your thing and whatever makes sense to you is really what I just want to go with you. The only other thing I want to write here, because I didn't write it here, is slope. Because we've been talking about y2, y1, stuff like that. This is formula for slope. It really is just rise over run. So I want to make sure you got that engraved too. Okay, I just want to move on down again. I want to try and see if I can get through this for you. Triangle midsegment theorem. Triangle midsegment theorem involves two things. It involves knowing what a midsegment is, and then it involves knowing what the midsegment theorem is. So first I want to define midsegment for you. And a midsegment is it's basically the segment that's drawn between two midpoints. That's it and that's all. If I have triangle ABC right here, pretend like this doesn't exist yet. I have triangle ABC though. I'm going to draw two midpoints, D and E. And the segment that's connected between them is called the midsegment. Now the midpoints is what divides these two guys in half, right? It cuts it right down the middle. It cuts this guy right down the middle as well. That's what the midpoint did. You find the midpoint. You can use midpoint formula, whatever it is you do. You find that midpoint, or they give it to you. The point is, what does this midsegment have a relationship with the rest of these two triangles? Because you'll notice here, I have two triangles. Here's a triangle in green, and then there's the big triangle that's in black right there. Now they have a special relationship. Notice the ratio here from CD. Here's CD. Let's say this length was x. I didn't know what it was. CA would be twice the amount, 2x. It's x plus x. Same with CE and CB. If CE was y, some unknown distance, CB would be 2y. So the ratio of sides here is 1 to 2. At least so far. We don't know yet that these triangles are similar. Well, actually, you know what? Because this is review. Yeah, we knew these triangles were similar. We proved that once. We did it. We did it back in February, you guys might say. Yeah, we did prove these triangles were similar. We proved it through side angle side. We said proportion, we got 1 to 2 side ratios, and then this angle was congruent to itself through a reflexive property. So the CDE is similar to CAB through side angle side. Now, corresponding parts of similar triangles, corresponding angles of similar triangles are congruent. It's not exactly CP-CTC, but pretty much the same thing. If I have similar triangles, that means all angles that correspond are congruent. So D is congruent to A, and E is congruent to B, at least as far as those triangles go. These are corresponding angles. Think of it like corresponding angles congruent. Here's a transversal. Here are two lines that pass through. If corresponding angles are congruent, then the lines cut by a transversal are parallel. So one of the points of the midsegment theorem will be, which I'm going to start writing, and the other one probably would have been easier to write because I was on a roll with it. But if a midsegment is drawn between two sides of a triangle, because we are talking about triangle midsegment theorem, then the midsegment is parallel to the third side of that triangle. Now, I'm not done. I'm going to say one more thing with that. But there's a good start. I'm actually going to put a comma there. Okay, if the triangles are similar, that means you do have a ratio of sides that is congruent or that's the same everywhere. So not only is CD over CA 1 to 2, and not only is CE over CB 1 to 2, but also DE over AB is 1 to 2 for the same reason. It has to be because these triangles are similar. Now, you might look at this figure and you might say, wow, DE looks a lot longer than half the length of that. Well, you might say that, but check this out. I'm actually going to literally copy and paste this. I'm going to drag this down and watch this. Paste. Paste. And you'll see, oh, geez, Mr. Robinson, you're right. That was half the length. I didn't draw it perfectly, but so there it is. That is half the length. So what I want you to actually put here, if you still have room or time to do it, if I can move these over for a second. Oh, yeah, I still have to put some more stuff in there. But DE, this length, will be half the measure of AB. In other words, if I have a length of AB, I cut it in half, I'm going to get DE's length. Not only that, but AB is also twice the length of DE, so it takes two DE's, like we just saw, to get AB. So you can look at this in either way. So the other part of the triangle midsegment that I'm going to put is not only is the midsegment parallel to the third side of that triangle, and the midsegment is exactly half the length of the third side of that triangle. Okay? So just some good stuff to know there. So triangle midsegment theorem says if you draw that midsegment, you've created not only parallel lines here, but this length is exactly half that, just like it divides these in half as well. So we are going to do a problem with that right now, by the way. I want to make sure that all that stuff was taken care of. Okay. True or false, determine if each statement is true or false, justify each of your answers. Some I won't be able to justify as well as others. I think if you hear me out, you're going to know what I mean, and it's kind of enough for you if you do that. If M is the midpoint of AB, here's A, B, and M. And we just talked about midpoints. It divides these guys in two right there. Then AB is congruent to MB. So they're asking, is this and this the same length? No, of course it's not the same length. If M is any closer to B than A is, then they can't be the same distance away from each other. No, that's false. B, if the diagonals of a quadrilateral are perpendicular, then the quadrilateral must be a rhombus or square. Now, I want you to be very careful about this because they aren't wrong when they say that squares and rhombi, which is plural for rhombus, a square and a rhombus both do have perpendicular diagonals. That's not something that I've talked about in this particular review, but they do. Now, that's not the incorrect part about this. I mean, this, if you tilt your head the right way, you're kind of looking at perpendicular diagonals there, and here, same thing, perpendicular diagonals if I draw it quickly enough. The only thing, though, is that this answer is actually false, and the reason is, even though these are perpendicular, notice what the wording is. Must. Must is the most important word of this sentence. Must means there is no other option. There is no other diagonal. There's no other set of diagonals that I can have that would be perpendicular to each other. And that's not true because we just did kites. And we know that a kite has diagonals that intersect at a perpendicular spot. Now, they're not perpendicular bisectors of each other like the rhombus and the square are, but a kite still has diagonals that are perpendicular. So here's the reason behind that being false. Okay, in part C, the diagonals of a rhombus divide the rhombus into 4 congruent triangles. That actually is true. I think I need to spare you the reasoning behind it because, to be honest, the reasoning involves a 2-column proof. I would have to prove that all the triangles are congruent first. It's not that hard. You need to do a reflexive property, alternate interior angles, vertical angles, stuff like that. It takes a while, though, and for the sake of time, like I said, I want to make sure that you know that property. Just know this straight up. Diagonals of a rhombus divide the rhombus into 4 congruent triangles. Yes, that's true. All the triangles have congruent parts. Here, here, and here. Not every part is congruent. Like, this isn't congruent to that in its own triangle. But these are 4 congruent triangles all right here. Okay, multiple choice. Circle the correct answer. You must justify each of your answers. Which of the following cannot be used to complete the conditional statement? And I want you to be careful. When you take this final, we are going to bold, underline, and italicize certain words and make sure that you pay close attention to the word. Cannot's a pretty easy one to pick up there. If quadrilateral ABCD is a parallelogram, then blankety, blankety, blank. Now remember, we're trying to find one that's not true. And in doing so, I want you to make sure that you know how conditional statements work. Conditional statements have if and then. And the if means if we assume this to be true. So you can't say, no, something's not going to be true because it's not a parallelogram. No, they tell you it's a parallelogram. Given the fact that it's a parallelogram, which of these things will not be true? Right? Which of these things would make the statement false? So I want you to remember something about labeling. They said quadrilateral ABCD. Now that has a specific purpose and intent to the way that they say that. You might be looking at these and saying, well, look, they didn't give me a drawing. How am I supposed to know? The way you're supposed to know is how you label these. It doesn't matter where I label A. I can choose any of these points. Let's say I choose it right here. Yeah, that works. The only thing that matters right here is that when you label these things, they have to go in sequence. So when I go to A, I must follow around to another side to find B, to another side find C, to another side find D, and go back to A. Or A to B to C to D to A. I cannot go A to B to C to D. I cannot go A to B to C to D. I must ring around the rosy, one direction or the other. So in other words, A and C, the letters that don't touch each other, must be on opposite sides of the parallelogram. And B and D, the letters which don't touch each other, must be on opposite sides of the parallelogram. I can put B here and D here. I could have put B here and D here. It won't change these facts that need to be true. For instance, AB is congruent to CD. That is true. Opposite sides of a parallelogram are congruent. That's one of the properties. AD is congruent to BC. Once again, opposite sides of a parallelogram are congruent. So these are, well, they're not false. These are true, but they don't give me the correct answer. I'm trying to look for the answer that would not be true. AC is congruent to DB. Now, AC is a diagonal. It's not false because the segment doesn't exist. The segment exists. It's just in diagonal form. There's AC, and there's BD. Are these the same length? To be honest, in a parallelogram, they are not the same length. Only in a rectangle and square are diagonals the same length. You can check it. We can check that kind of thing with coordinate geometry, but that's the one where you would fail out, and you'd say, if quadrilateral ABCD is a parallelogram, then AC is congruent to DB. That would be a false answer. Or a false then. False conclusion. The answer's correct right there. And by the way, AC bisects BD. BD also bisects AC there. But yeah, there you go. Number 3, which of the following can be used to complete the conditional statement? If quadrilateral ABCD is a rectangle, then ABCD is a trapezoid. No, see, trapezoids don't have two sets of parallel sides. That doesn't work. ABCD is a parallelogram? You betcha. I talked about that earlier over here. I wrote a sentence that started with, a rectangle is a parallelogram. So if you have a rectangle, then you have a parallelogram. It's just a specific type of parallelogram. Just keep remembering that when we talk about this. It's like, here's your rectangle, here's your parallelogram. It's just a skewed rectangle. It kind of moves that way a little bit. But it has parallel sides and everything else. Now, a parallelogram is not a rectangle. It doesn't work the other way, just like that human male thing. Okay? The converse does not always work. You have to make sure that you know which way you're looking at. Rectangle has all of the properties of a parallelogram. But a parallelogram does not have all the properties of rectangle because it does not have 90-degree angles. So again, just definitely something to keep in mind there. Okay, a few more problems here. Next page. Josh and Kelly are each trying to solve the problem. Determine if Josh, Kelly, both or neither is correct. Justify each of your answers. Okay, first I have one that says, assume that triangle MRO is congruent to triangle NPO. So before you do anything, you have to make sure that you know that they gave you the assumption. You can't say it's not true. They tell you it is true. They say it's true, believe it. Now, what I'm going to do first, before even doing anything else here, is I am going to correspond congruent parts. Because these triangles are congruent, CPCTC does exist here. And I want to match up parts based on the way that these letters are written. They're written in a specific way, and trust me, this is where it's going to throw you off. This diagram is not drawn to scale. If you thought it was drawn to scale, you would automatically match angle M with angle P, and you'd say they're congruent. Because they look congruent. I mean, they really do. Problem is, though, they're not. They're not because, well, we don't know they're congruent. Because M corresponds with N. Angle M in triangle MRO corresponds with angle N in triangle NRO, NPO. And in congruent triangles, the corresponding parts are congruent. So those two are congruent. R and P are congruent. Again, it might not look like it, but it's true. They told us that, so we must believe it. And O and O are congruent, if not for any reason other than their vertical angles. These guys have to be congruent. So maybe they'll trick you with the problem. Maybe they'll say something else, and you have to prove the triangle's isosceles by blah, blah, blah. Okay, not only that, but segment MR is congruent to segment NP. Segment RO is congruent to segment PO. And segment OM is congruent to segment ON. Again, CPCTC. That's all I'm doing here. So now that I have that all drawn up, I need to see if Josh answered this question correctly, if he set up a problem that can solve for x properly, if Kelly did, if both did, or if neither did. So the way to check this out is this length MO is 5x. Oh, you know what? Actually, before I even talk about x and stuff, I know that MO was congruent to ON. So MO and ON are congruent. I'll try NO. So 5x and 2x plus 8 are the same length. So if you write an equation that says 5x equals 2x plus 8, you're on the right track. Josh is good. He set up this question properly. Kelly, on the other hand, set up MO with OP. Now, MO and OP aren't shown to be congruent. See, this has 3 tick marks, this has 2 tick marks. So I don't know those are congruent. So Kelly set up an equation 5x equals 4 times x plus 7. That's not necessarily true. Sorry, I can't trust that that one's true. I can only trust Josh's. Trust Josh's. Josh is correct. The reason MO and NO are congruent. CPCTC. We determined that as we did this. Okay, problem B. How are the diagonals of a square related? This is something, again, I wouldn't really call it a no-duh, but you really do have side angle side going on here. If you want to start proving some stuff, you work through that. You have these two diagonals. Yes, these are congruent to each other. So Josh is correct when he says that. If you really want me to do it, do 2-column proofs. I can do it. Problem is, it extends 10 minutes of time on the video. Now, Kelly was also correct. Remember when we talked about these rectangles? The squares, rhombi, and kites all have perpendicular diagonals. Diagonals intersect perpendicularly. So Josh and Kelly are both correct when they say that. So you would circle both for that. Reason? Well, squares. I don't really know what else to say. Something we've talked about a lot before. That's really all I can say. I can do, like I said, if you let me do 2-column proof stuff with it, I can do it that way as well. For the sake of time, though, let's go and move on. Okay, for the following statement, determine if the statement is true or false. Justify your answer. So I'm going to first look at this statement here. If a quadrilateral is a square, then it has 4 right angles. I can't underline well, but that's true. I don't need to give a reason. Okay, step 2, write the converse for your statement. Now remember, a converse is the opposite of. Not the opposite as in if the quadrilateral is not a square, then it doesn't have 4 right angles, but flipping these parts of the statements that I can. Keeping the if and then where they are. Now, I'm actually going to type this one out. And then kind of just getting the rest as I may. So if, and I'm going to say if a quadrilateral, I'm going to flip the conclusion with the condition. If a quadrilateral has 4 right angles, then it is a square. So there is the converse statement. The question is it true? And I want you to think about it. Again, the things we talked about before. If it has 4 right angles, is it a square? Now, before you answer true or false, I want to make sure that you get that it basically is saying then it must be a square. That's really what they mean. It cannot be anything else. There's absolutely no other quadrilateral that I could name it. That is false. I want you to think about that. The reason is because there's this other thing called a rectangle. And a rectangle can is a quadrilateral with 4 right angles. In fact, I normally associate rectangles more with 4 right angle shapes than squares because I say that squares are rectangles that have all congruent sides. Rectangles makes that statement false, the converse. This one's true, that one's false. Okay, this one looks familiar, sort of. It's a triangle midsegment theorem problem. Solve for x, show all work. Okay, you are given this midsegment. You know it's a midsegment because they give you congruent parts here and here. We already know that when a midsegment is drawn, you have similar triangles. So similar triangles, you not only have parallel sides, but you have that 1 to 2 relationship here with similar triangles. So this is 1 to 2. It takes two 2x plus 7s to make one 9x minus 35. If that makes sense. So 2 times 2x plus 7 equals 9x minus 35. So, you know, the rest is algebra. 4x plus, 14 equals 9x minus 35. 5x equals 49, and x equals 9.8. You know, it's algebra. I'm not asking you to copy me down along with that. I could have done it the other way. I could have said 9x minus 35. 2x plus 7 is half of 9x minus 35. So I could have done this. But you can see why that might give me a bit of a headache. Maybe I don't want to work with that. Might give me trouble distributing the 1/2 into it. It's kind of messy. Either way is fine. Remember, it works no matter what. Okay, last page and last problem. Although there is a lot of work to be done on this problem. The most work, in fact. Look at because it's an entire page and you have to do a lot of calculations. Look at quadrilateral ABCD on the graph, and you'll actually notice they did say ABCD, and what I talked about with the rules of a quadrilateral are, wherever you start A, B must be right next to it. Then C must be right next to B, and D must be right next to C. And again, when it closes up, it goes back to A. So it goes A, B, C, D, A, B, C, D. So they followed their own rule. Awesome. Now, I don't know what kind of quadrilateral this is, and I don't want you to assume that it's drawn to scale. And even if it is drawn to scale, I don't want you to have to eyeball it. There's no confirmation that you can absolutely say that you know that any slopes, that any lines are parallel by their slopes, because these slopes might be different. You never know. It's best to calculate it, and that's what we're going to do right now. Find the slope of each side of the quadrilateral. So I want to find the slope of AB. And we can use that slope formula, but it's going to take me some time. So I'll use it once, and after that I'll kind of show you how it's a little quicker. The thing that would be easier for this kind of problem is just writing down your coordinate points as you see it. So I'm looking at these things. A is 0, 3, B is 7, 2, C is 2, negative 3, and D is negative 5, negative 2. Okay? So doing slope in the first one here from A to B, I'm going to take y2 minus y1 and divide it by x2 minus x1. That's 7 minus 0. So that'll be negative 1 over 7. So that's my slope there. Now that didn't take too much time. I'm just saying that sometimes that you have to reduce fractions and such. Well, we'll have to do it anyway. But that y2 minus y1, remember, that's just how much did it change? From 2 to 3, or sorry, from 3 to 2, it went down 1. I went down 1, then I went over 7. And that's really what I'm going to be looking at here when I do these problems. In fact, I'm going to keep those numbers up here because they're going to help me for the next set of problems. That's a 1, that's a 7. Little deeper there, 1 and 7. In green, I'll do BC. BC, it's all about rise over run, right? So technically I rise negative 5. I go down 5, and I go to the left 5. So those are 5 and 5. So it's down 5 over 5 to the left. Negative 5 over negative 5, my slope is 1 as you reduce that. CD is over here. From C to D, I go up 1. And I go over, well, I'll do it right here. I went up 1, I go over 1, 2, 3, 4, 5, 6, 7. To the left, though. Remember, in x direction, right is positive, left is negative. So I went up 1 over 7. I really should put negative 7, but right here I have to put negative 7. There's my slope there. And finally, AD, let's get a different color. From A to D, well, I'll go from D to A. I'll go up 1, 2, 3, 4, 5, and over 1, 2, 3, 4, 5. So that's 5 and 5. So up 5 and over to the right 5 is 1. So those are my slopes. Good. Find the length of each side of the quadrilateral. Use the Pythagorean theorem if necessary. Show all work. So I gave you these notes before. I talked about distance formula. You could do it if you want to, but we've actually technically already done some of the work. You don't need to do all of this because you'll notice we just did some x2 minus x1s. We didn't actually calculate it like that, but we counted like that. So like I said, you don't need to actually do it this way. That's going to be a little topsy-turvy for you. You could do it like Pythagorean theorem. Do some counting. In fact, I already did the counting for you. We've made right triangles. Check this out. There's a right triangle. I can find the length of AD by using Pythagorean theorem. All I have to do, I'll do it right now for you, is DA is 5 squared plus 5 squared equals this length, DA squared. A squared plus B squared equals C squared. It's Pythagorean theorem. So that's the setup for that problem, and I'm going to get that length by doing that. I'll do it the same with all the other ones because I am up here and I want to see it. Let's just go this way. But again, I'm just going to use Pythagorean theorem for all of them. That's really what the distance formula is. So 1 squared plus 7 squared equals AB squared. So 1 squared is 1, 7 squared is 49. 49 plus 1 is 50. So AB squared is 50. AB is the square root of 50. Now the square root of 50 is the square root of 25 times the square root of 2. Square root of 25 is 5. Square root of 2, square root of 2. So it's 5 root 2. AB is 5 root 2. Okay? BC, what which green I used? BC right here is 5 squared plus 5 squared equals BC squared. So 25 plus 25 is 50. Square root of 50, once again, same thing. Square root of 50 is 5 root 2. Looks like I'm on a little bit of a roll there. So this is 5 root 2. And I'm kind of going to save you the time on this one. I want to make sure that you can kind of, when you recognize I want you to make sure that you can save time on something when you recognize a pattern. I think that's important, that you're not just having short-term memory loss on everything, and that you can really notice when you see a pattern in something. Like I could start setting this up. I'll go 1 squared plus 7 squared equals CD squared. And you start to say, I've seen these numbers before. Why keep doing the math when I know where it's going to lead to? This was 1 squared plus 7 squared equals that. My final answer ended up being 5 root 2. So CD is 5 root 2. And I mean, you don't have to do that. I'm just saying for the sake of the video, I shouldn't have to slow down on things that you can do on your own at that point. And the last one, DA, it's the same thing as BC was, 5 squared plus 5 squared. So your final answer there will also be, just like the other ones actually, it's going to be 5 root 2. These are all in units, by the way. They didn't give us centimeters or anything. So all of these here are 5 root 2. You can start making your own conclusions, but I want you to keep going just so you know exactly what shape this thing's going to be. Because obviously they're going to ask you, and I want you to know in the end. Okay, part C. Draw the diagonals of the quadrilateral, then find the slopes of the diagonals of quadrilateral A, B, C, D. Okay, so I have to draw the diagonals, and remember, you can draw a diagonal from A to C. That's what the diagonal is. So I'm actually going to make it really thick, though. I want to make sure you can see it. Thick and orange. Let's do orange. From A to C, it's going to look, like that. And from B to D, what's a unique color here? Let's get yellow, a darker yellow. C to D, or B to D, I have that right there. So those are the diagonals. And what we have to do is find their slopes. Now remember, slope is this y2 minus y1 over x2 minus x1. If the numbers get too big, you can start doing that. Just for the sake of practice, let's do that. Let's find the slope of AC. Y2 minus y1, 3 minus negative 3. 3, whoa. Let's change that. Let's do 3 minus negative 3, which is 3 plus 3, over x2 minus x1. Let's go 0 minus 2. And that equals 6 over negative 2, which is negative 3. I'm going to put negative 3 over 1. It's going to help you in the end to write slopes always like that, because then you know exactly what you're referring to. BD, same thing. y2 minus y1 over x2 minus x1. B2 minus negative 2. That's 2 plus 2. Over 7 minus negative 5. 7 plus 5. So that's 4 over 12, which is 1/3. Okay? Part D, are the diagonals of quadrilateral ABCD perpendicular? Justify your answer. The way you're going to figure this out, you don't want to eyeball it. You don't just want to say yes because it looks like it. It's all about the math. We talked about the math before. Diagonals, not diagonals. When you have two slopes that intersect, and two lines that intersect, and their slopes are opposite reciprocals of each other, like these two right here. This is opposite reciprocal. Negative 3 over 1, positive 1 over 3. Opposite reciprocals. When you have that, you do have 90-degree angles right here, 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 and here. So the question, are the diagonals of quadrilateral ABCD perpendicular? Yes. Why? Opposite reciprocals. You can put check slopes. Whatever it is. As long as you determine and show me somewhere what those slopes are, I think you're in the clear. So we do have opposite reciprocal slopes there, so the diagonals are perpendicular. Final question. What type of special quadrilaterals ABCD clearly explain? Okay, I want you to look back at everything we've done so far in this problem. Let's start with the slopes. This is slope AB right here. This, AB, and CD have the same slope. AB and CD have the same slope. So in a quadrilateral, right now, we are at least looking at a trapezoid, right? We have one set of parallel sides for sure. Boom. Now we compare BC and AD. Well, BC and AD also have the same slope, right here and here. So now we're at least looking at a parallelogram, because a parallelogram is opposite sides reciprocal. Both of them are. Okay, now let's check out lengths here. We have 5 root 2, 5 root 2, 5 root 2, and 5 root 2. All sides are congruent. Boom, 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 boom. They're all 5 root 2. What does that mean? I have a shape with opposite sides parallel, all sides congruent, and by the way, just let's save time here. We already know the diagonals are perpendicular. We know that's true in a kite, but in a kite they don't have all sides congruent, and opposite sides definitely aren't parallel. This is a rhombus. Right now, we are looking at a rhombus. Now, the only way that, see, how do I say this? This could also potentially be a square. Okay? The way that you determine that it's not a square is by looking at these original slopes again. You have to compare negative 1/7 to 1. These would have to be opposite reciprocals of each other, right? Because in a square, remember, is a rhombus with 90-degree angles. I wrote that right here. Square is a rhombus with 90-degree angles. For these angles to be 90 degrees, these slopes need to be opposite reciprocals of each other. For instance, if this was negative 1/7, this would have to be 7 over 1. But it's not. So this angle is not 90 degrees. Because it's not 90 degrees, because it's not a square, and because it's not a square, it is a rhombus. So my clear explanation will be quadrilateral ABCD is a rhombus because why? Because opposite sides are parallel. All sides are congruent, and the diagonals, I can't spell, are perpendicular to each other. This is not a square because the sides are not perpendicular to each other. So that explanation is good for me because you showed the math to reveal that information previously. So it's not like you need to say all the stuff that you said before, like, oh, opposite reciprocal. You already said all that stuff, or it's kind of hinted at when you did all this work. If this was the only question that was there, you'd have to do all this work prior to that and then get to that part, or at least do that explanation. Okay, I'm going to check the timing on this thing. I think I did better than last time. I think I sped up, which is totally awesome. Totally happy for that, and trust me, it is a load off my back to feel like I recorded it again. I was kind of angry at myself the first time, and now I feel much better. I hope you guys feel well about this material. This is all that's encompassing in Unit 7. Yay you if you get the stuff, seriously. And if you do have any questions, I would love you to ask. Otherwise, thank you for watching this video. I don't enslave 2 hours for no reason. I want you guys to watch these things. I want you to do better. All right, so enjoy you being you.